So last time we introduced this Gaussian approximation, which goes beyond this static homogeneous mean field theory of a Landau's free energy. And there we try to calculate this partition function by this functional integration of all these coarse-grained mean field order parameters, which shows the spatial variations in space. And we neglected this quadratic term, this phi to the power 4 in this Landau's free energy functional, which is the expansion of this order parameter field. And we only keep this expansion up to second order in phi, which is what we call the Gaussian approximation. And under such approximation, we are able to calculate this partition function and this free energy and also the thermodynamics. And today we will rigorously calculate this two-point correlation function, the Green's function that we did for the Ising model in the previous lectures. But today we will perform the functional integral and use that kind of a functional integration to derive this two-point correlation function that we already derived by the shortcut method, meaning from the equipartition theorem in statistical mechanics. But here we will more rigorously derive such a correlation function. So what we are interested in this kind of a ensemble average or thermal average of this product with two order parameter fields, 5r and 5r prime at two different spatial locations, and we can Fourier transform this kind of a phi-phi correlator. And what we need to compute is the thermal average of this k-space correlation function, phi k prime. And of course, this follows the standard definition in statistical mechanics, ensemble average. So in the denominator, we have this, say, partition function, so which we already derived last time. And this partition function is nothing but the product of all this functional integration over the phi in k-space. And in the integrand, it is this Boltzmann weight e to the minus beta L, and L is our Landau's free energy in k-space up to the Gaussian approximation. So, but in the numerator, we should multiply all this multidimensional functional integration by this product phi k prime. So that's the standard definition of this ensemble average. So the denominator is nothing but a trace of this e to the minus beta h here. H is actually this Landau's free energy functional, and the numerator is the trace of this e to the minus beta h times a, where a is some kind of statistical observables. So now we simply just plug in this Landau's free energy functional in k-space and plug into definition of this phi-phi correlator. And once we plug that in, effectively what we need to evaluate is just this double integral over d phi k and d phi k prime, where k and k prime are kind of a momentum index of all these different k values in Fourier space. Well, this momentum that we want to evaluate is actually belong to two of this n or infinite number of momentum points, which we call this k and k prime. But this integration runs from, say, phi k1, phi k2, and phi k3, up to phi kk and also phi kk prime, and all the way to the very end of phi kn. But only two of these momentum indices are involved, which are this phi k and phi k prime. All the other momentum integrations are decoupled from these two momentum integrations. So we could simply forget about all the other degrees of freedom by keeping only this d phi k and d phi k prime in this integral. So the resulting integration is given by this line here. We have this kind of a Boltzmann weight as function of phi k and also phi k prime in the numerator and also in the denominator. And in the numerator, we have this phi k prime. And the range of integration over d phi k and d phi k prime are both from, say, minus infinity to plus infinity. And to make progress, you can think of these two cases. Case one is when k is plus or minus k prime. And the first case is when k is is not equal to plus or minus k prime, or k is independent of k prime. And the second case is that when k is actually equal to plus or minus k prime, whereas k depends on k prime. So we'll see later that the first case, when k is related to k prime by a plus minus sign, then we get something. Okay, so in the first case, when k has nothing to do with k prime, then you could easily factorize this integral into two independent integration over d phi k and d phi k prime. Right? Okay. Since phi k has nothing to do with phi k prime. Okay. So you could separate this double integral into two separate single integral, and you look at the single integral here where you have this phi k times e to the this phi k square exponent, and from the symmetry of this integration, you know that this phi k is actually odd function of phi, because when phi goes to minus phi, you get a minus sign. And integration is from minus infinity to plus infinity, so that there's a cancellation ranges of this integration, minus part of the plus the positive part. But you could very easily see that because the odd parity of this function, remember this exponent actually is a function of phi k magnitude square, which is even function of phi. But this single phi k multiply within this integrand is actually an odd parity in phi. So the even function in phi multiplied by the odd function in phi equals the odd function in phi. Okay? So as a result, by the symmetry argument, you easily see that this is 0. So which means that if k has nothing to do with k prime, then you get 0 of this correlation function, which is good. And the second case is when k is related to k prime by plus minus. So we should compute this separately depending on whether k is equal to plus k prime or minus k prime. And for the plus one, we should compute this phi k square without the magnitude. For this minus sign, you should calculate phi magnitude square, because this is given by phi of k, phi of minus k. And you know that this phi minus k is actually the complex conjugate of phi of k, because this is a Fourier transform of the order parameter field. And so this is nothing but phi of k magnitude square. So let's take a short break. When we come back, we will separately compute this phi k square and also the square of the phi k magnitude average and see what it leads to. The only contributions to get the non-zero these correlation functions come from these two cases when k is the same as k prime or minus k prime. So let's just talk about this first case when k is k prime. In that case, in general, this phi of k is actually a complex valued variable, or order parameter, and has this magnitude and phase. And let's just denote this magnitude by this absolute value of phi of k, and the theta of k represents the phase of this phi of k field. And therefore, the integration over this phi k square ensemble average is actually proportional to this integration over this phase multiplied by the integration over this magnitude, which we don't care the magnitude at the moment, but we just look at the phase integral, the theta of k. But this is phi k square, not the magnitude of phi k square, and this phase is actually added. So phi of k times phi of k is going to be the magnitude of phi k times, say, e to the 2I theta of k, right? Because these two phases should be sum over. So they are not cancelled. So therefore, if we integrate over this entire angle of theta of k from 0 to 2 pi, and this integration of e to the 2I theta of k gives you 0. So that is the complete integration over a sine or cosine theta of k, which vanishes. And this leaves the only possibility to get the finite value is that when k is minus k prime. In this case, this phi correlator is given by this Kronecker delta function, delta k plus k prime, and this gives you 1 when k is minus k prime and 0 otherwise. And the integration to be evaluated is actually this absolute value square of 5k. And therefore, there's no angle integration involved, only the magnitude. Of course, if you only compute this magnitude integral over this d phi magnitude, then of course it will lead to the finite value. And we could actually take advantage of this Gaussian integral, and you could define this variable z, which is the magnitude of 5k, and you could actually use change of variables from this d magnitude of 5k to dz or dz square. Then you could easily check that this integral gives you precisely the same form as we obtained by a shortcut, which is coming from this equipartition theorem. So we can Fourier transform back to the real space to see this phi-phi correlation function in real space and how it behaves. So we can actually transform back to the real space from this k-space phi-phi correlator, and it leads to such a momentum sum of this Fourier transform this function. Of course, you could obtain some kind of a numerical results by integrating over this momentum variables. Okay, but you could check a simple limit, which is the static limit when k equals 0, or you could simply just perform this real space average of this phi-phi correlator in real space, and you simply just can actually perform such a real space average pretty easily, which leads to nothing but k equals 0, or in a uniform situation where you simply just take the real space average of this phi-phi correlation function. And that Green's function in real space, gr r prime, or g as function of the distance r minus r prime, is nothing but this kbt times this isothermal spin susceptibility that we introduced earlier. So once we get this Fourier transform, this phi-phi correlation function, and you could Fourier transform back to the real space, and you get nothing but this isothermal susceptibility. Okay, so now we complete the circle, and this is again consistent with what we have found either, say, in the Ising model or in this kind of a Landau's free energy functional. But here we include the Gaussian fluctuations. Remember, we start from the mean field theory by neglecting this spatial variations of the order parameter phi, and we obtain some predictions which we call the mean field theory predicted exponents. But now we include the spatial variations of this phi field, but we neglected this quartic term. And so by doing so, we include the spatial fluctuations of this mean field order parameter in our calculation, and we arrive this Gaussian predicted critical exponents. So we'll see in just a moment that this Gaussian approximation will actually revise or correct this naive mean field predictions regarding these critical exponents. But still, this Gaussian approximation is not good enough because it neglects this quartic term, which becomes more important as you reach this critical temperature. And also, this perturbation theory will break down as temperature reaches Tc. And so we will find a more systematic way to actually improve this Gaussian predictions. So the Gaussian predictions somewhat seem better than the mean field predictions, but still is not good enough. So the way to actually fix this problem is by using this renormalization group analysis of the full Landau's expansion of the free energy up to the quartic term. Okay, the simple perturbation theory fails even if we like to include this quartic term beyond the Gaussian. But as we'll see later, that this kind of naive simple perturbative expansions still fails as you reach to this critical temperature Tc. So we will discuss that in more details, but nevertheless, we should continue this calculation and get all these critical exponents, say beta, gamma, and alpha, and so on, within this Gaussian approximation. So let's take a short break. When we come back, we will continue and finish up this other predictions within this Gaussian theory. So before the break, we calculate the Green's functions or correlation functions in real space, and we found the previously derived results for the isotomal spin substitutability. So now we take advantage of such Gaussian approximated results, which gives the free energy of this form, the log of this function of this k written here, and we try to evaluate the critical exponents within the Gaussian approximations by using this free energy from this Gaussian form, okay, of this Landau's free energy. Functional, and specifically, we would like to check whether we could reproduce or give different results from this mean field predictions regarding the critical exponents alpha, beta, gamma, delta, and nu, which we already defined over there. And also there's a called anomalous exponent eta, which appears in the real space Green's function in this exponent 1 over r to d minus 2 plus eta, where eta is non-zero in general. But we'll see that within the Gaussian approximation, we have some trouble getting that non-zero value of eta. And based on what we just derived before the break, this isotomal spin substitutability, and we could very easily find that this gamma is actually 1, and actually based on this Gaussian approximated form, this Landau's free energy functional, it's easy to see that this correlation length also diverges as t to the minus 1/2. So nu is actually 1/2, and beta is also 1/2. That is identical to this Landau's mean field theory, and delta is 3. Nothing's changed from this mean field prediction. The only thing that is shifted from the mean field prediction is the specific heat divergence in a different power from 0. So in the mean field theory, this is actually a jump or discontinuity at the transition, which leads to alpha being 0 because there is no power law involving here at the transition for the specific heat within the mean field theory. But here, we'll see in just a moment that this alpha within the Gaussian approximation is this different value from 0, but still this value is not good enough. But at least this is the kind of improvement of this mean field prediction. So let's just focus on the specific heat calculation, which is defined by second temperature derivative of the free energy, and the free energy is given by this Gaussian form. And we simply just plug into this definition of specific heat and taking the second temperature derivative of the free energy and close the transition temperature. This temperature derivative is very close to reasonably approximated by this 1 over Tc times partial little t. Remember this little t is actually T minus Tc divided by Tc, absolute value. So, but this is the kind of a cumbersome job to evaluate this temperature derivative to second order. So I simply skip the details and just outline the final results. Okay, so the final results for the specific heat is given by the sum of the two terms A and B. A is given by this summation over momentum of that function, and B is given by a different momentum sum of different k-dependent function. So you could check how you get these two summation of different function A and B, and we will show later that this A always dominates over B integral, so that the specific heat is dominated by this A integration. So this is what we will analyze more closely, and at the end of this calculation we'll check whether B could be neglected. Okay, of course this B should be neglected. And so let's just look at this A integral. So the A integral involving this kind of a momentum sum, whereas momentum, the absolute range of this momentum is limited to the inverse of the lattice constants, 1 over a, and you could use a continuous integration to replace discretized moment and sum as the system goes with thermodynamic limit. And we could rewrite this in terms of the momentum integral over a d-dimensional k vector. So to see the divergence in this a integral, we need to rescale this variable k in order to really see how this vector can diverge. To that purpose, we introduce a rescaling of the momentum variables by a factor of c, and where this c later we'll see that this is nothing but the correlation length, which will diverge at a transition. So then we could rescale this momentum k by a factor of c, and then we rewrite this integral in terms of the momentum variable q, which is a rescaled momentum. And the integral ranges from 0 to a cutoff, which is this momentum cutoff lambda times this correlation length c. Okay, so this q is actually a dimensionless quantity because this k has a dimension of momentum and c is a length scale, correlation length. And so q must be dimensionless because up to some prefactor this momentum is actually inversely proportional to the length scale. So that this upper cutoff lambda times this correlation length is actually a dimensionless quantity. So then we should focus on how this kind of a bracket integral, which I defined this as integral I, how this integral I diverges as we close to the transition temperature where this correlation length diverges. So we should monitor how the thing inside the bracket diverges at the transition. So that's our job to check. So let's take a short break. When we come back, we will analyze how this thing diverges. So let's do the power counting on the specific heat as temperature close to Tc. And as I mentioned, this specific heat is dominated by this integral called I, which is in a rescaled form given by this kind of an integration over dq. And so as this little t close to 0 at the transition temperature is reached, and this correlation length diverges, and we should examine how this factor I diverges as the limits approach. And so we could actually do the power counting of this function of q, since this q integration is from 0 to infinity, so it may be divergent or may not be divergent. So it depends on dimensionality. So if you look at this factor, this integral dq divided by 1 plus q squared and everything squared, and if you look at this powers of q, as q goes to infinity, where it could diverge there, you could actually see very easily that this is proportional to q to the power of d minus 1 minus 4, which is d minus 5. And this integral converges when dimensionality d is below 4, the upper critical dimension. So of course, when q goes to 0, you could see very easily that this function 1 plus q squared remains finite, which is 1 in the limit of q goes to 0. So, and that limit will not lead to the divergence of this integral. Okay, so the only place where this integral could go divergent is when q goes to infinity. And that's how we do the power counting when q goes to infinity, by power counting this powers of q in the numerator and denominator. So you can very easily see this condition, to get this convergence of this integral. And in fact, if you evaluate this integral numerically, you'll find this is just a finite value, okay, some constant. And therefore, you can forget about this integral over dq, when dimension is below 4, and just look at this prefactor, which is proportional to the correlation length power of 4 minus d. And you can see very easily that the specific heat diverges as the correlation length to the power of 4 minus d, where d is less than 4, which is a positive exponent, positive power. And therefore, as little t goes to 0, this c goes to infinity, and so is the specific heat. go with that correlation length to infinity. So we could actually extract this kind of a divergence in specific heat as the temperature reaches the transition temperature. And so, but if you look at the origin of this divergence of this integral I, which in the original form in that integral, if you look at how this and why this integral I diverges, and you'll see the origin of this divergence is because when k goes to 0, so that this integral is actually proportional to the correlation length to some power, and this will lead to divergence. On the other hand, when k goes to infinity, this will not lead to a divergence. So if you look at the origin of this divergence, and it diverges only when k goes to 0 limits, and which we call that this is so-called infrared divergence. And the infrared refers to the fact that this momentum goes to 0, or the wavelength of this kind of a quantum particle, which is inversely proportional to the wave number or momentum k, goes to the large limit. So which falls into some kind of an infrared wavelength of light. And so this is called the infrared divergence. And so we could easily find out what this divergent power or exponent of this power law divergence in specific heat as a function of little t to some power, and this power can be obtained easily from these two expressions there. So the correlation length diverges to t to the minus 1/2, but this c is actually proportional to t to the minus alpha, and we know that this is given by this 4 minus d as exponent of the powers of the correlation length. So that leads to this alpha value, which is 4 minus d divided by 2. Okay, so this is the Gaussian predicted specific heat divergence exponent, and this is different from this 0 of alpha within the mean field theory, and we didn't derive this 0 of alpha within this Landau's mean field theory, but you could easily derive such a result based on this Landau's mean field theory of a free energy functional, and then you can compare these two, and it looks like the Gaussian approximation improves the mean field theory predicted value of zeros of alpha, but still this prediction is not good enough, because we know the rigorous results for the two-dimensional Ising model, where this specific heat goes logarithmically dependent on this little t, as little t approaches 0 at the transition, leads to zeros of alpha for a two-dimensional Ising model, a very rigorous result. But if you plug in this d, it's actually 2, you get 4 minus 2 divided by 2, which is 1. So there is a large difference between this Gaussian predicted alpha and exact result of this two-dimensional Ising model. So likewise, for a three-dimensional system, alpha should be 1 or close to 1, but this Gaussian predicted alpha is just 1/2. So there is still a large discrepancy between this Gaussian predicted value and the more exact result. So we will address that issue later, but at least we get something different and from the mean field prediction. So that's for dimension below 4. And what about the dimension above 4? So to see this, we should go back to this original form without the rescaling. So the original form of the C specific heat dominated by this integral A goes like this. So again, we could actually do the power counting, and by separating this integral into two parts. One is, say, from 0 to the very small value C inverse, assuming that C will diverge near the transition, but in fact it will not diverge, and we'll see in just a moment why it will not diverge. And this is the part of the integral, and plus a second part, which is from, say, C inverse to the cutoff momentum. And we call this the first integral 1, and second integral 2. And we could do power counting for the first integral. and simply just integrate over this momentum and plug in this upper and lower limit of this integral, and you get this is actually non-divergent if the dimension is actually above 4. So because this cutoff is actually very large, and if above 4, so there's some kind of 1 over lattice constant, which is again a finite value, but this correlation length will not diverge. This c to the power of 4 minus d goes to 0 because c may be large, but if d is large enough, larger than 4, and this c to the power of 4 minus d will converge. And the second integral, again, it's very easy to see that this will remain finite as c goes to infinity. So then when dimension is above 4, the leading contribution to the specific heat is just a finite constant. But of course, there will be subleading term contribute to specific heat, which is the function of temperature, which we don't care, and which will vanish when d is above 4. So we combine these two results for dimension below and above 4, you get this behavior specific heat. And translating to this Gaussian predicted exponent alpha, you get 4 minus d divided by 2 when dimension is below 4, and 0 when dimension is above 4. Okay, so that's the complete story of this Gaussian approximation. And of course, we need to show that the second integral, remember, c is actually a plus b. And what we just analyzed is that the a integral dominates over the b, but we haven't shown that this b integral is actually subleading or negligible compared to this a integral. And we also do not have time to show that this transition temperature Tc will get a shift under the Gaussian approximation relative to this mean field predicted transition temperature Tc, and this may become your homework exercise later. So we are just about to end this chapter, but before we end, I will spend a few minutes to show that the remaining integral b is indeed much smaller than the integral a. So let's take a short break. Okay, so let's just finish this analysis of this divergence of the specific heat within the Gaussian approximation. And as I mentioned, this specific heat c is dominated by this integral a. What about this integral b? And the b is defined by this integral, which we call this j, and which is given by this momentum integration, where its denominator is just k squared plus c minus 2 as the power exponent. And again, we rescale this variable k by defining this dimensionless variable q, which is the correlation length times this momentum variable k, and we could rewrite this integral j and do the power counting once again. And this time, this integral over the q behave as q to the power of d minus 3 when q is large, and it vanishes when q vanishes when dimension is greater than 1. So we can actually summarize this divergence of this integral j by these two cases. The first is when d is less than 2, then this integral j indeed diverges in the power of t to the minus 1 minus d over 2. But if you do the power counting of this divergence in j compared to the divergence of this a integral over there, you see that this is still negligible compared to the leading divergence of this a integral over there. So in that case, even though this integral b diverges when dimension is less than 2, but we can still neglect this integral b because this divergent power is actually much less severe than the divergence of this integral a. And when dimension is above 2, and this integral j remains finite when k goes to 0 limits. Of course, when k goes to infinity limits, this integral converges. But in any case, when d is above 2 and the whole thing of this j integral remain finite, so which complete our circle that this integral b takes a subleading role and can be neglected near the transition. So the final remark is that we just derived the Gaussian approximation and derived the exponents within the Gaussian theory, but the question is whether we can observe such critical exponents in the real experiments. And the answer is no. Why? Because for a simple reason we just explained earlier, that as this temperature approaches Tc or little t goes to 0, we inevitably we cannot avoid go beyond this Gaussian approximation regime. Because you remember this Ginzburg criterion is reached when this little t is actually within the range of this Ginzburg criterion, or TLG. So within this little range, this quartic term 5 to the power 4 is needed. We need this quartic term to actually correct this kind of Gaussian approximation, but the Gaussian approximation by definition neglect such a quartic term, which is needed when we really reach to this transition temperature. So in other words, you can maybe observe such exponents out of this critical region, but as you go to very close to critical temperature, and this Gaussian theory breaks down. So you never really observe such critical exponents in the real experiments, because you can never, this Gaussian approximation can never be the correct theory within this Ginzburg criterion, or within that little thin shell, or this kind of a critical region. And that explains the difference between this Gaussian predicted exponents and the exponents that either derive rigorously or observed experimentally. So there's always finite differences between the observed critical exponents and the Gaussian predicted exponents. And precisely because of this inevitable critical region, that the Gaussian theory must fail. So let's conclude our chapter 7, and on Thursday we will start a new chapter about anomalous dimensions, which will account for the anomalous exponent of the Green's function. Remember this eta appearing in this correlation function, our Green's function, in terms of the real space distance. And then we will formally go to the kind of a breakdown of the Landau theory and how to actually improve this Gaussian approximation by including the quartic term through this randomization group analysis. And otherwise, I'll see you on Thursday.